Okay, we have here the sum from n equals 1 to infinity of 1 over n times n plus 1. Okay, pretty straightforward. I think I might need to do some things to kind of complicate this. What I want to do to start, I think we need partial fractions on this to split it up. What I can do with this one, and actually I probably should have just left it there, but anyway, for 1 I can write it as n plus 1 minus n. And then if we rewrite it and we split this up into two terms, breaking it on the minus sign, we have n plus 1 over n times n plus 1. And actually, I'll leave it all in one sum. So the second term is going to be n over n plus 1. Cancel n's here, cancel n plus 1's here. And then what we're left with, let's just clean it up. We're going to have 1 over n minus 1 over n plus 1. And then I think let's do an index change on it. If I just add 1 on all the n's, I just need to subtract 1 over here. Doing that, this becomes a 0. And then let's just clean up everything else. And now to overcomplicate it, we're going to use the Digamma function on it. Let's just look at our series expansion for the Digamma function. Okay, now looking at our formula over here to the right, our input in this isn't a 2, this is a z right here. So our series that we have over here, everything's really the same, but our input, the value that we need to worry about right here is this 2 right here. So in order to rearrange it to work with our sum, let's just add this. This is the Euler-Mascheroni constant. It's about 0.577 approximately. And then this way we've isolated the sum and we can get it and we can rewrite it in terms of the Digamma function. So coming down here, what we're going to get using this is going to be Euler-Mascheroni constant plus Digamma of this input right here, which is just 2. And then let's just see if we can simplify this. Now for Digamma of 2, we have this formula that allows us to reduce it, this kind of recursive formula. It's going to be Digamma of z plus 1 is going to be the same thing as Digamma of z plus 1 over z. So here, working with Digamma of 2, we reduce it by 1, and we get Digamma of 1 plus just 1 over 1, or 1. And then I think it's a good idea just to kind of remember this value, because when we reduce eventually, if it's an integer, we're eventually going to reduce to Digamma of 1. For Digamma of 1, this is just going to be minus the Euler-Mascheroni constant, so we can write this value, Digamma of 2, as 1 minus the constant. So plug this back in here, we're going to get Euler-Mascheroni constant plus 1 minus Euler-Mascheroni constant. This here is going to cancel, and what we're left with is just 1. Now, one thing I should mention before we finish up, there's definitely, I can't think of too many ways, but I can definitely think of at least 2 ways right now, and there's definitely a way to do this without using the Digamma function. One thing we can do is just start listing out terms. So plugging in when n's 0, this is going to be 1 over 1 minus 1 over 2. Plug in 1, then we're going to have plus 1 over 2 minus 1 over 3. Let's just write out a few more terms and see what's happening. And so now what's going to happen here is we can cancel half with minus half, third with third, fourth with fourth, fifth, sixth, and this is going to cancel with some other term down here. Now what's going to happen, at some point you would have some terms that don't cancel, but the only thing is this is going off where n's infinity. When n is infinity, you look at this limit, these last values are going to be just 0, so we don't care about any of that. We just have one term that didn't cancel, and that's just a 1. So for our solution of this, we just get 1, the same thing we found over here. Okay, there you go. That's it for today. Thanks everyone for watching. Have a good day.